Does he want you to read the full things or?
Yeah.
Oh, because it's like no one really reads the full research papers. That's just bad time management. Read abstract, read results. If they're interesting, then read them out.
So you need to summarize them, write a report.
Right now.
Well, I mean, all the, like, each of the papers are like the same thing. It's just written a
Well,
little
yeah.
differently. It's all the same research.
Right now I'm handing out papers for my intro and lit review, so.
Huh?
Is that all the topics for the rest of the semester?
I hope so. Well, originally it was planned for 30 lectures, 2 meetings per week. Methanol?
Oh, yeah. You can have some real fun with methanol.
Who is ethanol?
I'm ethanol.
You took it first. I mean, if I really wanted to, I could have put an IPA on. That's more fun.
Sorry, I'm about to try it.
Depending on your interpretation of abbreviation IPA,
Isopropyl alcohol.
one can discriminate whether it is a chemist or a drinker. Could be India Pale Ale.
I mean, you can drink IPA, but it'll cause you some severe toxicity.
I'm convinced.
Yes, but you actually can absorb small amounts of methanol. So you do actually have to be semi-careful with that.
And
Is it aren't they all single root replacement reactions? Like still. Yeah. This week was actually really
Hey Beth, when you want to get
just like dissolve compound, put it in different solutions.
oh, that lab, that one epically failed.
Really?
My TA said he it didn't fully dissolve at first, so he kept on adding nitric acid
Oh god.
to the point where we asked him, so how
So
much
if
did
you
add?"
were not perfectly happy with previous homework, this one should be great. This one should make you happy for sure. And my handwriting is not perfect, so do not be too excited in the following sense. If you do see sloppy symbol like this, it should read like 100, not like 400.
Oh, I like that one.
I see an optimist immediately.
Well, no, this time they had to like dissolve it.
Trusted a bunch of freshmen with concentrated nitric acid.
Yep. I don't know. I was like, what? I'm like, all right. And first of all, I couldn't find it anyway. And it was all in like one post. All the nitric acid except for one vial. And I was like, yeah, that was like, I'm just sit here with it because I don't trust you guys.
No, so Seth kept on adding more and more to the point where Ethan, my partner, we asked him, so how much did you add? He's like, I shit ton. So we asked him, can we put that in the lab report? He says, well, I said it. So we're like, okay.
No, when I did it, I was so scared because I was dissolving in like a test tube.
SMU speakers.
Well, no, in our for the like I did a demonstration for like a lot like one of the first week labs, and so they wanted to show all the gas coming off of it, so like the test tube held the gas more. And I was so scared it was gonna like foam over because it started like, it was like dissolving fine, and then all of a sudden
Oh my
it
god.
rapidly dissolved, and I was like, and they're all like, oh, sick. I'm like, oh, don't spill over, don't spill over, don't spill over, don't spill over. I was like, I do not want to clean that.
Well, our next lab, it says we wanted
You didn't use
UMOS
anything.
sulfuric acid.
All right.
Keep coming
Oh,
late.
it's all
It's like boil until white bean.
Oh, yeah.
Yeah.
Oh, okay, well, I feel that week is coming to completion. Friday will be very soon. And we do have the important event on Friday, which, again, you are doing it by preview, but it is one of the most important parts of the course, and you will not regret it in regarding the extracurricular grades. So please plan to email the PowerPoints, the slides for your presentations by midnight of Thursday. It is needed in order to process them, to maybe print them for others to read, and for having things ready here. Because we have very limited time and we need to present them quickly. So, if you were not in the day of votes, if you didn't practice democracy, then you will get a little complicated subject because no one voted for it. Enter. So plan on coming to the lab and preparing the subject. Okay. So I will not change the subjects. They will be as they're written here. Maybe the order can be swapped a little bit for better logical arrangement. For example, the last one could be migrated a little higher up in the list. So please plan on 180 seconds, which is very limited. So if you, it is physically not possible to present more than 4 slides. So it's a big challenge to, main idea of these presentations is that each person becomes expert in one subject and then shares expertise with others. History of success or failures. But even if you are very well prepared and you know what to present, it is a big challenge to squeeze your knowledge into few slides and few words. I cannot brag that I do this every time before the lectures, otherwise we would complete the course in 2 weeks. So it's, you'll be champions of squeezing information. And this is not the last time you will see this code. It will be used for little individual research projects in the next month. So if you were not among the volunteers who come at Wednesday evenings, the subjects are approximately split onto principles of solving time-dependent algebraic equation in discrete representation, numerically. Next chapter is a way to analyze and represent the observables that are computed in this methodology. And third one is applications of these methods to a couple of simple systems. And so that you do not feel yourself blind in the individual projects, the range of practically important systems will be much broader. You will select yourself with some help what to choose and what to explore with the same methodology. On Monday, I plan to announce new homework, and when the notes will be distributed, you will see it will be less challenging than previous than the previous one. And we will, it will be due next Friday, 10 days from now, and during the next week we will focus on the subjects. So it will be not, well, probably in a natural way, no one will start doing it ahead of time, and there is nothing wrong with it. So you can wait until Monday and just accumulate your spirit. So who we are, what we are doing, and what is our revision section. So we are in the physical chemistry class. The goal is to predict outcome of experiments and observables of several methods to characterize molecules and materials. We got the fundamentals of quantum theory, and we are getting more and more fundamentals as we go. And we are applying it first to simple systems, and there is a hope that before the semester ends, we will apply it to something practical. So we are done with particle without any potential, particle in the square box of any realistic dimension. So we are not considering 4 or 5 dimension. And right now we are analyzing if any quantum features affect vibrations of molecules and other systems that exhibit vibrations near the equilibrium. One of the questions to the homework that will be in the far future is give the list of all systems that exhibit oscillatory behavior. And we went through metal plasmons, of course, protons and any molecules that vibrate for infrared spectroscopy. What else did we count? Like radio receiver. One can make a potential for electron to oscillate. And there is one important example for those who have a physics minor or major. If you look on the laser, then it is electromagnetic wave which is confined, same as our electron is confined. And it has limited number of maximum nodal points inside between the resonators of the laser. And the amplitude of electric field there changes in time in a harmonic way. So in some sense, one can consider the amplitude of electric field inside laser resonator as another harmonic oscillator. It is very far from chemistry, but almost everything in this world oscillates. So it's not a big challenge to give examples of what does oscillate. So here are the Lie vibrations for polar solvents. And if we develop potential energy, which is just square function around the equilibrium, and we do want to prepare components for our future fun reactions. Our fun reactions will be predicting the time evolution, but before we need eigenstates, eigenfunctions, and some background knowledge of the mechanical knowledge of this quantized oscillator. So we are slowly but surely going through eigenstates. And solving the Schrödinger equation for oscillator is possible through series expansion, and I intend to share it in the form of handouts, but believe me, it is harder than things that we are doing. And it is less scientifically intuitive. So it is just like a solving mathematical problem and waiting until one can analyze. In what we are doing, we are making a bypass through weather operators. We are doing little small steps, and we are able to analyze scientifically what we are getting. So what we are doing is more intuitive and helpful for understanding the things that we are describing. Never forget normalization. And through philosophy of science, through annihilation of a vacuum, we were able to solve this equation and develop the ground state of quantized vibrations, which is a Gaussian wave function with some normalization which uses square root of square root, right? It is good for you if you memorize it, but I can't require it because I'm not able to memorize it, but that's not. Now, we are going step by step to get the next states. Through our concept of weather operators, which we composed, and I will review them in a minute, we hope that applying creation operator to this ground state, we are going to obtain the first excited state. So it's very, very simple. Right? Okay. So last time I was a little lost and I tried to find the logic for exact coefficients in front, and I decided to check myself after our meeting once again. And one of the requirements for the weather operators for creation and annihilation is that if we multiply them, creation by annihilation, and multiply by the frequency times Planck constant, it should reproduce the Hamiltonian, it should give energy. And I was making check that square of the coefficient in front of position should give this dimension of energy times the frequency times potential and kinetic potential, and for the momentum part that it reproduces the kinetic part. And one can formulate these operators in several ways, which will not affect the way they change wave functions. The only important things are that the proportionality between factor in front of position and momentum is m omega. And the rest of coefficients can be changed without much loss of generality. What is important and what I can memorize, and I think you can memorize, is that the coefficient in front of, so weather operators, both of them, are linear combinations of position and momentum operators. Okay? And the momentum operator comes with imaginary unit factor, and when we switch from annihilation to creation, we swap the sign because we want to have it Hermitian conjugate. And one can put factors, all factors, out of brackets, and inside the brackets have only this proportionality and imaginary union. Also, what one can notice is that if it is little plus here, then there is minus here and opposite. If there is nothing here, there is plus there. So those are operators that help us to avoid solving complicated differential equations, that allow us to simplify mathematical challenge. Later on, we will see that they give a little bit of scientific insight as well. But original goal is to avoid hard equations. Okay, so what do? We hope that acting by the creation operator onto, if I go so quick, we will finish 2 arrow. So if I act with this operator on our ground state, which is Gaussian in respect to displacement from equilibrium, then we should get something that is very well expected by all our beliefs in this course, that will represent the first excited state. So it is the only operation that we are going to do today. So we will just, we are going to replace momentum by its definition, which will be first derivative, and then apply first derivative to Gaussian function. That's it. We do not have any more plans for the medium, because we are going to have much more stress or pleasure or just intense events for the lab session tonight and your presentations on Friday. So take derivative. The momentum is first derivative, right? And if we plug it into there, then the imaginary unit gives factor -1 and minus square -1, and then there is 1 minus that was originally here, and another minus from definition of momentum. So it should change to the plus sign. So the factor of mass and frequency times position plus h bar and derivative over the position. And all factors can be called normalization, and we will take care of them separately. If we are too enthusiastic, we can process them, but how did I came with minus? Check once again. Let's count together. What should be the sign? So we do have minus here by definition. Then we have minus I from momentum operator, and that's it. What will be signed here? -1. Please check. Right? Good. Error. Minus. So we do not care much about these factors. We can just put them out of brackets and combine whatever they represent. And now we are taking a derivative of the Gaussian function, right? So there are two terms. In first term, we multiply Gaussian function by a factor mass, frequency, and position. And in second term, we are taking derivative. So first term, neither multiplying by a factor nor taking derivative of exponential are changing the exponential. So just to keep shorthand notation, we can keep it outside of the brackets. Then factor doesn't change, and taking derivative yields the factor that was in the power of exponential coming up front, and then it is a derivative of r squared, right? What do we see then? I had a fear that the terms might cancel and we will get 0, which will look very strange. But if you would get 0, it would mean there is no excited state. But let's check it carefully. So there is factor 2 because of derivative. There is factor 2 from the power of exponential. Then there is a Planck constant from definition of operator and from the factor. And then see, the terms are the same. M omega position, mass frequency position. But the sign here, minus times minus, gives plus, right? So we can just put factor 2 at the front. Yeah, very close to moment when we can depart in peace. So normalization times position times E minus omega r squared. So let's plot this function. How should it look like? You can draw in air. Yeah. So it's product of two functions, and we can. So how do we plot functions if you do not have computers? If suppose that we live 80 years old or more, when nothing can help us to plot. No, since we are humans and we are plotting for humans. Well, of course, you can take the paper with grid lines, compute by pen and paper value of function at each point and put points. But it is boring. We do not need this precision. It's humans who make images for humans. So we should catch just major features of the functions. And major features of the functions is to identify where the function is 0, where it has maxima, where it has minimum, and where, what else? 0, maximum, minimum, and which sign does it have? 0, extrema, and sign. So this can be done by multiplying functions, just in our head. So if we draw the phi 0 function, this is Mexican sombrero head, right? So it is 0 at minus infinity, 0 at plus infinity, and it has maximum at 0, right? Then we have the linear function. So it has infinity at infinity, minus infinity at infinity, and we have plus, minus, and it has 0 at 0. So, which points we can place on this graph right away? What will be the, we do not need to know much, we know just multiplying anything by 0 will be 0. Right? So what will be the value of the resulting function at point 0?
0.
Good. What will be the value of the resulting function at plus infinity?
0.
What will be the value of resulting function at minus infinity?
0.
Good. I'm so happy. We have a consensus. Now, what will be the product of one positive function times another positive function from 0 to plus infinity? Sign. Positive or negative?
Positive.
Positive. What will be sign of the function in the from minus infinity to 0? Negative. So just, you do not need to be very precise again. No? A little more precise. Let me try once again. Opa. Right? Yes. So, and the approximate area of space where the function is substantially bigger than 0 should correspond to the same area for the ground state. So I'm going to try to redraw it. Once again, so it is very close to 0 here. Make this exercise in the vicinity of 0. So how does it compare to other functions that we know? Well, you know many functions. I'm not challenging your knowledge. In the functions that we know and play with in the course, how does it compare to first excited state of the one-dimensional box, which is ground state is half period of sine, and first excited is one full cycle of sine. Do you see any correspondence?
It's flipped. Or it's shifted the phase.
There will be nothing wrong if we redefine it without flip.
Doesn't matter.
So, what is different and what is similar?
If they are constrained.
Yes, for the box it is constrained.
Or
It is constrained more. This one is constrained less because it approaches 0, but it never is never literally 0
okay.
at the edges. So it has some slowly asymptotically decaying edges.
I was just saying the vast majority of it is constrained
Yeah,
within the
majority
space.
is very similar. While for the box we choose this parameter, and for oscillator we also choose it. Well, we not choose it by free will, it is dictated by the frequency and mass of things that are oscillating. What else? How many nodal points here and there? How many places where a function is literally no nodal points where it crosses, not approaches 0 but crosses 0. One here, one there. So now let's project it to our memories. Well, again, I'm not looking on your members of your whole lives. One of the things in the course. Remember Bohr model, momentum, and density of fringes. And by the way, someone of you is presenting real and imaginary part of wave packet. I don't remember it from the top of the head, but it's also connected. So if we have a quantum particle which is moving, it means the wave has fringes. And the quicker particle is moving, the denser are the fringes. So it crosses zero more and more frequently. If it doesn't cross zero at all, it means it doesn't move. Stay still. If it crosses zero, it means it wants to move. Well, maybe it wants to move, just bouncing back, forcing back between walls. So just looking on this shape of wave function, we can tell that it has some kinetic energy. So this wave is moving, forcing back, while the ground state looks like it stays still. And same here. So the kinetic energy for the excited state is not zero. So from this analogy and from this connection to our memories, can we expect what will be the next excited state? How many nodal points should it have?
2.
Yes. So if you're sure about it, you can skip Monday meeting. We will take another, we will apply the creation operator once again and get this second state. And we will also work on the normalization carefully. Although we didn't hit the limit for today's meeting, it will be not possible. It will be a little more extensive in time and amount of derivations. And it is a little early to finish everything, but a little too late to start new section.
So here's a question.
Yes?
As you said, if it doesn't cross the zero, it doesn't want to move. But when it does cross zero, it likes to move. So if it crosses zero twice,
It moves more vividly.
Okay.
The amount of kinetic energy is higher.
Okay.
And we already talked about sombrero. And we already multiply the functions. There will be a big discovery that I will set up as a discovery, but you all know it. That the energy of ground state is one half of the frequency, and when we jump to the next step, the energy will change by frequency times Planck constant. This result can be obtained both in standard, traditional, canonical way of solving the time-independent generator equation for harmonic oscillator, or it can be obtained in our insightful approach, but not immediately. We can do it, but let's postpone it a little later. Basically, we will just normalize, make sure that our wave functions are ready to find any observables, and then we will just take expectation value of Hamiltonian if the Bra and Ket are ground state, or if the Bra and Ket are first excited, and then we will get this result. But now it is too early to go through this derivation step by step. But if we do this offset, like wave function plus energy, then you get the figure that you recognize in 100%. Every textbook reproduces it. So it makes offset proportional to energy and then draws these functions. Whenever I was borrowing time from you, now I'm returning. So everyone is invited to visit the lab section this night from 5 to whatever it takes, hopefully before 7. And I look forward to see your PowerPoint slides in my email box before midnight on Thursday. Meeting is complete. I will stay here to answer any questions.